Yep, can you hear me?
We see you, but we hear you not.
Yep, no, we've got it.
Hi. Okay, right. I think you can see me and hear me now. Yeah? Good. Well, I apologise again for the technical problems, but thank you for coming and welcome to the Dyalog webinar. If you're watching on dialog.tv, you can comment and ask questions in the chat thing down the side, and we'll try and respond to those as we can. Now, today I'm going to be talking about Advent of Code, which is a programming competition that's been running for the last 4 years. It runs like an advent calendar, so every day for the first 25 days of December, there's a new programming puzzle for you to solve. And the point of the competition is to try and solve these problems as quickly as possible, and each day you can get points for solving them fast, and then there's an overall leaderboard to track how you're doing throughout the month. But last year, well over 50,000 people took part in this in one way or another, and I can guarantee that most of you had no interest whatsoever in winning points or trying to win the competition. And even the guy who created it, who's called Eric Wastel, his advice to people is ignore the leaderboard, just have fun solving the puzzles, use them for fun and education. So that's what we're going to do today mostly. I've been playing this for the last 3 years now, and I have accumulated some tricks to try and help me work quickly, so I will talk a bit about those as we go along. But mostly what it boils down to is trying to think clearly and keep things simple. So try and keep your environment simple to avoid distractions, and try and keep your code simple so that you can work effectively with it. A colleague of mine once said that debugging is a waste of time, and it's time that you've wasted twice over, because first of all you had to write some incorrect code in the first place, that was a waste of time, and then you have to spend time debugging it afterwards, which is another waste of time. So I want to try and focus on, as I say, simplicity and clarity of thought, and the hope is that if you have a really good, clear understanding of the problem you're trying to solve and how you're trying to solve it, and if you can understand every part of how the code you're writing fits together, then maybe, just maybe, you won't need to spend any time debugging it afterwards. And I can guarantee that if you are up against the clock, that is a really big saving. Debugging your code after the fact can be a huge time sink. Now, I said I'd recommend keeping your code simple, but I want to emphasize that that doesn't necessarily mean keeping it as short as possible, like you would in a code golf competition. And it doesn't necessarily mean splitting it all up into tiny pieces that are all named with meaningful names. It's more about making sure that you write the code in a way that really makes sense to you and that you can understand deeply. And some good litmus tests for this are, firstly, for a reasonably small problem, can you understand every part of the solution you've written and keep it all in your head at the same time? If there's too many details and messy bits here and there, you probably won't be able to understand it all at the same time. Another test is, could you explain your code clearly to another person without too much of this umming and erring and, oh yeah, well I had to do that because this bit doesn't quite do what I want. If you can explain it all clearly without too much hesitation, that's a good sign that you understand it clearly yourself. Now, writing simple, clear code isn't easy, but practice makes perfect. And my suggestion is that spending a bit of time up front to try and clearly understand the problem and your solution and the code you're writing will pay dividends later when you don't have to spend that time debugging your code. So, to get started, let's take a quick look at the Advent of Code website. Here it is. There's not much to see on the front page except for this calendar, which has got the days of the month from 1 to 25 up the side. And if I click on one of these, day 1, it takes us to a page for the puzzle for day 1. And you'll see quite a lot of prose describing the puzzle. You'll see some sample inputs, some examples, something telling you exactly what you have to submit as your solution. And then down the bottom it says, to play, please identify yourself via one of these services. And this is a really important thing. The really, really cool thing about Advent of Code is that it doesn't matter what programming language you use. You're free to solve the problems in any way you want, using whatever setup you want, any programming language you want. You might even occasionally find a puzzle where you don't need a computer at all, and all you need is a new sheet of good white paper and a sharpened pencil. All that matters is whether you can submit the correct answer for the problem. And because it is a competition and they don't want you copying other people's answers and cheating that way, what they do is they explain the problem, but then they have some input to the problem which is unique to your login. That's why you need to identify yourself and log into the site. So it means that even if the program you end up writing is very similar to someone else's, the input you get will be different, so the answer that you have to submit will be different. And the great thing about this is it means that I'm free to do this using Dyalog APL, and I can compete with other people who are using Perl or C or Python or whatever they want to use. So I'm going to identify myself to the website. I'm going to use my GitHub account for this, and I can do this because I've previously told GitHub that I trust the Advent of Code website. So if I log in via GitHub, you can see that I'm now identified on the Advent of Code site as Foad. And if I scroll back down to the bottom, there's a link where I can get my puzzle input. And this is the input that is unique to me. If I click on that, I find a very simple text file. All of the puzzles have this kind of input. It's a simple ASCII text file, which I'm going to save to disk. I'll call that day1.txt. And then the first step in solving any of these problems is going to be reading the input from that text file. So let's hop over into APL and see how to do that. So this is my APL setup. I'm using the RIDE user interface on Linux. I'm running Dyalog APL version 17.0 here. And if you remember what I said about keeping things simple and avoiding distractions, let's see if we can get into more of what John Scholes used to call a Zen programming frame of mind. John spent a lot of time testing the RIDE user interface on his Mac, and whenever we added something to the user interface, he'd always say, "That's great, how do I turn it off?" So let's see what we can do. We can go to the View menu in RIDE. We can turn off the language bar, gets us a bit more real estate. We can turn off the status bar down the bottom, and we can even, here there's an item on the menu, toggle full screen, F11. That's toggle full screen. And here we are with something pretty close to a white sheet of paper. I think we're fairly free of distractions now. We do still have a scroll bar down the side, but that's a bit harder to turn off. I've loaded an initial workspace, which is something that I tend to use for all of the problem solutions that I'm doing live. This has got a few useful things in it. It's got the entire contents of the dfns.dws workspace. So you can see there's a whole load of utility functions in there. Not because I need them all, but because occasionally there's one that I do need. For example, there's a very simple function in there called to, and if I want the integers from some number to some number inclusive, it's nice to have that. It's better to have these here and not need them than to need them and not have them. I also have some utility functions of my own devising. Usually these are things that I've needed for previous puzzles, and I tend to accumulate this in this workspace so that if a later puzzle has something similar to a previous puzzle, then I don't have to reinvent little utility functions that I've already created. An example of this is the sort function. There's an idiom here. This expression on the right is an idiom that lets you sort an array of any rank. And rather than have to remember exactly how to type that, I have a sort function that will let me do that easily. And the third thing that this workspace has done is to enable a couple of settings that I like. One is boxing, controlled usually by the box user command, which means that if I have nested arrays, I see them in boxed output. And the other one is the rows user command, which is a handy way of making sure that if I generate a lot of output on one line by accident, it doesn't take up loads of my screen. You can see it's nicely truncated towards the right hand side of the screen. Now, what did we come here for? We had saved some puzzle input, and I wanted to show you how to read that into APL. Now, for all of the kind of input processing that you'll need for this kind of puzzle with simple ASCII text files, I would highly recommend that you learn to use quad nget for reading files in, and quad R and quad S for any sort of simple processing of the input that you need to do. So, first stage is to read the file using quad nget, and the magic incantation for this is to take the first of the quad nget of the file name and a little flag which is number 1. So the 1 on the end means please give me this file of lines as a nested vector of character vectors. So I get 1 character vector for each line in the file. That is almost always what I want, to the point where personally I think that that should have been the default. And the reason for the first at the beginning is that quad nget actually returns more than just the content of the file. It returns the content and then some information about the character encoding and so on. In this case, I'm only interested in the content, so I just want the first item here. So this has returned a vector of character vectors. So the first line of input was this 3 character vector minus 16. Of course, for doing any kind of calculation on this, I don't want character vectors, I want numbers, so I need to do typically some kind of processing on the input. In this case, every line just defines a single number, so it's as simple as doing an execute each on this data. So typically, I would start with something like that to get the input to my puzzle. Now, what do we actually need to do with this? Let's go back to the puzzle page and have a look. Now, there's a bit of an art to reading these puzzle descriptions. You might notice that it's quite verbose, and if you have plenty of time, by all means read the introduction and read the story. There's a nice thing about Santa and his elves. If you're in a hurry, you might like to learn exactly which bits you really need to read and which bits you don't. In my case, I've kind of learned that you can normally skip the first couple of paragraphs. I would suggest skipping down until you see some term written in bold, maybe. The kind of things you're looking for in the description are anything that tells you what your puzzle input is. For example, it says, the device shows a sequence of changes in frequency, brackets, your puzzle input. So I know that that list of numbers that I was given is some kind of changes in frequency. A value like +6 means the current frequency increases, a negative value means the frequency decreases. Okay, that's pretty simple. For example, here's an example of an input. If you had +1, -2, +3, +1, starting from a frequency of 0, you would apply those deltas. So you'd apply a delta of +1 to get to 1, -2 to get to -1. Okay, so I'm starting to get the impression that the puzzle here is to add up a list of numbers. Here are some other examples. +1, +1, +1 results in a 3. Yep, okay, adding up the numbers. And finally, down the end, another thing in bold that you should pay attention to, starting with a frequency of 0, what is the resulting frequency after all the changes have been applied? So the puzzles usually end with a statement like this, which tells you pretty unambiguously exactly what kind of answer you need to submit. And occasionally this is very important, like if it boils down to finding the longest string in a list or something, you need to know, do you have to submit the longest string, or the length of that string, or its position in the list? Because it is very, very frustrating if you essentially solve the puzzle correctly, but then just end up giving the wrong kind of input. It will tell you you're wrong, and you can waste a lot of time trying to figure out why. So, in summary, I would suggest you read anything that's in bold, anything that's got an example of an input or an output, and definitely the bit at the end that tells you exactly what you need to submit. So in our case, I've got the impression now that I need to add up the numbers and I need to submit the total number. This is quite easy to do in APL. Let's use plus reduce. I reckon the answer is 472. because I have already played this particular puzzle and solved it, instead of, if you hadn't played it, you'd get an input box here where you type in your answer and click submit, and it will tell you if it's right or wrong. In my case, it's telling me you have already solved this one and the correct answer you gave was 472. Is that what my APL said? Yes, 472. Now, each day's puzzle on this website is actually in two parts. Once you've solved part one and got the correct answer, it kind of unlocks the description for part two that you can see here. And part two of the puzzle normally builds on part one, so it will use the same input and the same kind of ideas, but you'll need to solve a different problem on the same kind of theme. So this is a little bit more involved, so let's read it a bit more carefully. The summary is, you need to find the first frequency that it reaches twice. So they're going back to, I think, probably the same example they started with, starting with a frequency of 0, applying each of the deltas in turn. So the resulting frequency after one step is +1, after two steps it's -1, then it's 2, then it's 3, then it's 4. And then we get to a frequency 2, which we have already seen earlier in the list. So that's the kind of thing we're going to be doing. This immediately says to me that rather than a plus reduction, we're looking at a plus scan kind of thing to get all the intermediate results. There's some more important stuff in the description. Note that your device might need to repeat its list of frequency changes many times before a duplicate is found. So what it's saying is that the list of inputs that we had, so we had a list of 1,000 numbers, you might need to apply that list more than once. Once you reach the end of the list, it cycles round back to the start of the list. So you might need to run through that list more than once before you find the first repeated value. And there are some more worked examples you can use, some more examples here that you can use to confirm your understanding of the puzzle. So the kind of thing I'd be looking at for this is it said you start with frequency 0 and then apply all the deltas. So maybe if we start with a 0 followed by a plus scan of the puzzle input, that would be a good thing to start with. I'm going to name that. And then the trick is to look for the first value in that list that appears, that has been seen before, or the first value that appears more than once. Now, there are lots of ways of doing this. I'd certainly be very interested in what springs into your mind first. What came into my mind first was using dyadic iota. In fact, using what we call an iota selfie. Iota selfie Q, or Q iota Q, will tell me for each item in that list of partial sums Q, at what position was that value first seen. So if all the items in Q are unique, then that will just be the numbers from 0 to 1,000, or however long Q is. If we find an item in Q that has been seen before, that particular item of the result of the iota selfie will be some smaller number. It will be the position where that value was seen the first time. So, like I say, if they were all unique, you might expect that the iota selfie on Q matches iota tally Q, that is the indices of all the values in Q. And in fact, in this case, that is true. So what about if we ask, what is the first place where those two things do not match? Well, at the moment they all match, so we're not expecting any ones in that result. But let's say we're going to keep extending this list, and we're going to keep going until we do find some ones in this list. What's a good way of finding the position of the first one? Or, we could do that. We could try and look for the position of the first one, and the primitive function where will tell us that. Or perhaps, since the answer we want to give is which value was first seen, perhaps we could use this mask to compress Q, and then that will give us a list in order of all the values that have been seen more than once. So, as you'd expect, at the moment this list is empty, but why don't we start applying the list of deltas more than once, as the puzzle description hinted. So P is a list of length 1000, I think we saw before. What if we reshape it to have length 10,000? Then we're going to get the same list repeated 10 times over, and then get the partial sums, and then look for the first repeat. Well, they're on to. How about if we just assume that we understand what we're doing and keep going with this process until we do find some duplicates? Reshape it to 100,000. What if we reshape it to 1,000,000? So now we're applying that list of deltas 1,000 times over in total. And now look for the first repeated items. Aha! And now we find, if you repeat it enough times, we do find some duplicates. The very first value we found that was seen more than once is this guy, 66932. And sure enough, if we look back at the puzzle, your puzzle answer, the correct puzzle answer that I've previously submitted in this case, was 66932. Now this is fine if you're just playing along with the competition, maybe trying to solve it live and get an answer as quickly as possible. But it's what I call a kind of interactive solution to this problem, yeah? Because I didn't know in advance how many times I was going to have to repeat the list of inputs. So I kind of had to keep trying things in the session until I came up with an answer. Like I say, that's fine if all you want to do is get the answer. But you might also like to think about, you know, what if you wanted to publish your solution? If you wanted to publish it, or if you wanted to give it to somebody else who might have different puzzle input that might need a different number of repeats, how would you write this such that the program kind of stands alone and doesn't need the user's input to try and work out how many repetitions you need to find a valid answer? Now I'm going to leave that as a question for the viewer. I'd be interested to see what you come up with. And incidentally, I will show you later on the idea of publishing cleaned up solutions. And this idea of cleaning up your code and, you know, coming up with something that you're truly happy with, that you feel you understand and are completely happy with every aspect of it. This is something that Roger Hui sometimes refers to as monument quality code. The idea is that it's something that you're so happy with that you would not be embarrassed to see this solution carved in stone and inscribed on some monument that's going to last for thousands of years. Now, I'm certainly not at that stage yet with this solution, but you know, it's something to aspire to when you think about publishing solutions. Now, the actual APL code that we wrote for day one was not all that challenging. We've seen how the site works and the kind of thing you'll have to do. But let's move on to another problem to get another example of the kind of thing that you have to do for some of these problems. I'll skip on to day two. I don't want to solve too many of these today, but let's have a look at day two. Now, again, reading the puzzle description is a bit of an art. I'm not going to read all of this because it's too long. But again, looking for the bold parts in the puzzle description. We're going to get a list of what it calls box IDs, and we're going to be looking for similar box IDs. Okay. Where does it say about your puzzle input? Well, it tells me here I've got a list of likely candidates, my puzzle input. I assume that means candidate box IDs. And then here we go. So it's talking about counting the number of IDs in my list that contain exactly 2 of any letter, and then separately counting the ones that contain exactly 3 of any letter, and then you can multiply these 2 counts together. For example, if you see IDs like this, so I'm getting the idea that the list of IDs is going to be a list of character strings like this. And it's talking about some of these strings containing a character that occurs exactly twice or exactly 3 times. So it says this one here contains 2 A's and 3 B's. Okay, some of them contain a character that's repeated twice. Some contain a character that's repeated 3 times. Okay, so let's take a look at the puzzle input. Again, I can get it down here. I'll save this to a text file day2.txt. I will switch to my APL session and I'm going to read my puzzle input again. First of the quadang get of day2.txt 1. So there is my list of strings. Let's call that P again. We've got 250 strings, and just out of interest, how long are they? Okay, it looks like they're maybe all 26 characters long. Yeah, so I've got 250 strings, and they're all the same length. And back to the puzzle description. For part 1, it's asking me to find out how many of them contain a letter which appears exactly twice, how many contain a letter which appears exactly 3 times, and then I need to multiply those counts together to get my answer. In this example, it was 12. So, for any puzzle like this that is asking you about counting the number of unique occurrences of a letter, I would naturally start thinking about the key operator. And I would suggest one of the things that you have in your kind of mental toolbox is to be familiar with the simple cases of using the key operator. Even if you don't use all its full generality, even if you don't care about the dyadic cases and the high rank cases and whatnot, there are some very basic cases that you probably ought to be familiar with. And I'm talking about cases where there is one simple vector, say a character vector argument on the right, and the operand function to key on the left is one of a few simple cases. For example, a good way of understanding what key does in this situation is to give it a left argument function of just alpha omega. That's essentially just showing you what the inputs to the operand function are. The result of the whole key expression is then going to be a matrix, because the result of this operand function, that pair alpha omega, each result of the operand function gives you 1 row of the result of the whole expression. So here we have 4 rows in the result. Each row corresponds to one of the unique items in the argument. And in this case, we get a 2-column matrix where the left column, which came from this alpha, tells you what the unique item was. So in this case, it's a letter, M, I, S, or P. And the right argument gives you the list of indices where that letter was found. So the letter M was found at index 0, the letter I was found at indices 1, 4, 7, and 10. So that's good for understanding what key is doing. You might not care exactly where the letters occur, but as in our case, you might be more interested in how many occurrences they are. So if I ask for the tally of omega, that's just going to tell me how long that list of occurrences was. So this tells me that M occurred once and I occurred 4 times. So this is getting closer to what we want. Actually, for our strings, all we really care about is, was there any character that occurred 2 times or 3 times? We don't even care what the character was. So we could just say tally omega key. So this is looking good. This tells me that something occurred once, something occurred 4 times, and something occurred twice. This is looking like the kind of thing we need. So then to answer the question, did any character occur twice? Well, yes, it did. That was the P. I think that occurs twice. Did any character occur 3 times? No, none of them did. Not exactly 3 times. So, going back to our puzzle input, what we'd like to do is for every string in that input, we'd like to apply this key expression. So tally omega key on each item of P. Incidentally, I said these are kind of basic cases of the key operator. They're also, the trivial cases are ones where there is special code supporting them in the implementation of key, so they should all be pretty efficient. So if I do this tally omega key each of P, that will tell me for each string in the input, what was the list of repeat counts of each character in that string. So I could say, I could ask for each string, was there a 2 in the list of repeat counts? And it looks like almost every string had a 2, had some character that occurred twice in it. Was there a 3? Okay, so most of them don't, but you can see there the ones in that result tells me that there were a few strings that contain a character that occurs exactly 3 times. So at this point, I could name this result and try and work out, is there a 2 in each of Q, and then maybe find out how many of those strings have got a 2 in their result, and then maybe do the same thing, how many of them have got a 3 in that result, and I'll get the right answer. But I've got a funny feeling at this point. I'm sensing a pattern. It's a little bit ugly that I have to name this intermediate result Q. The pattern that I'm sensing is I'm trying to find out if there's a 2 in each item of this list Q, and I'm also trying to find out if there's a 3 in each item of this list Q. So the pattern that I'm feeling is an outer product kind of thing, because the result I want is some function of all combinations of the number 2 and 3 and the vector of vectors Q. Yeah? And when I say outer product, I mean jot.f for any function f, regardless of what that function is. The outer product pattern is you have two array arguments, and you're interested in doing some operation on all possible combinations of one thing from the left argument and one thing from the right argument. So what I'm feeling is I've got 2, 3 on the left, I've got jot.something, and on the right I've got my vector q, which I now that I'm only mentioning it once, I no longer need to name. I could write it out longhand. Tally omega key each P. And what is this function that I'm trying to do on all combinations? Well, I just want to know if 2 is a member of each of those lists, or if 3 is a member of each of those lists. So let's have a look at that. Each row of that is now telling me which of these strings had a 2 in and which of these strings had a 3 in. I want to count each of them. Now that I've got my data in this form, that's absolutely trivial. I just want the row sums of these the 2 rows of this Boolean matrix. And now that I've got those 2 numbers, what did the puzzle say? Count how many you've got a letter that occurs twice, count how many you've got a letter that occurs 3 times, and multiply those numbers together. So a times reduction. And that gives me the answer that I want. 4,980. Your puzzle answer was 4,980. Now, I'm not saying that it's necessarily essential that you code your answer as a one-liner or that you spot all these abstractions. But the reason I like this solution is because once I started naming Q and then writing the same kind of expression twice, this plus reduced to as a member of each of Q, plus reduced to as a member of each of, 3 as a member of each of Q, it started feeling like the solution was messier than it needed to be. This solution down the bottom, I kind of feel like I can explain every moving part. You know, there's no fat in this. I can tell you exactly what every part does. And, at least in retrospect, I can explain every part of this and be happy with it. Let's just quickly take a look at part 2 of the same puzzle. So part 2, of course, uses the same input file, and it is now talking about IDs which differ by exactly one character at the same position in both strings, for example. So this is their example input to demonstrate what we need to do for part 2. And it's saying we're looking for 2 strings in this list that differ at exactly one character. And it's telling me that in this example, the ones we're looking for are FGH, IJ, and FGU, IJ, which only differ in their middle character. Now, I think the problem description here is actually telling me something about my data, which is that there is going to be a unique solution. There's nothing in my data that says there couldn't be more than one pair of strings that has this property. But I'm sensing from the way the problem's described that there is going to be a unique answer, and that's the one they want. So let's just go looking for a unique pair of strings in my input P that have this property that only one character differs between them. Now, I previously showed you that all the strings have the same length, which is very useful because we don't have to worry about, well, what happens if you have a string of 5 characters and a string of 6 characters? How many characters are different between them? So I know that problem doesn't arise. So the interesting thing about this is that part 2 of the puzzle is another outer product. It's a different outer product, but still, what we want to do is we want to exhaustively search all combinations of 2 different strings from the list that I've been given in P. And the normal pattern for doing this is to do an outer product of some function where both the left and the right argument is my input P. Typically, to avoid repeating myself, I'd do an outer product selfie. Yep, jot.fqb on P gives me all combinations of 2 strings taken from P. So the only question then is, what is my function going to be given 2 strings? Well, so I'm looking for 2 strings that differ in exactly one position. So your first thought might be to take the 2 strings you're given, look for characters that differ between those 2 strings. That will give me a Boolean mask of the positions that differ, and then we want to find ones where there is exactly 1, 1 in that Boolean mask. So if we do a 1 equals plus reduce on that mask, that should do the job. Before I hit enter, I'm just going to want to get a handle on how big this result is going to be. We had 250 strings in our input, so this is going to be a 250 by 250 Boolean matrix. I don't want to print the whole thing, so for now, let's just have a little look at the top left corner of that matrix. That's interesting. It's all zeros. That means that there are not very many strings that differ by exactly 1 character, which is a good thing. We were expecting there to be exactly 1. So what else can we do to get a handle on this result? Let's ask, where are the ones in this matrix? And again, we're expecting exactly 1 answer. This where function works on Boolean arrays of any rank, and it will give you, if you give it a higher ranked array, it will give you kind of coordinate tuples into that array where the ones are found. So I'm free to use this on a matrix, and well, that's interesting, isn't it? I didn't think carefully enough. I said I was expecting a unique result. Of course, the outer product considers all pairs of strings from the input, and it will give me the pairs in both orders. So what this is saying is string number 58 and string number 202 have this property that they differ in exactly one character, but of course so does that pair of strings in the other order, and I should have expected that. I should have thought of that. Anyway, I can proceed from this point. I can say, okay, well, just give me the first of those, and then maybe I'll try and use that vector 58202 as some kind of index into the original list. So maybe I'd even do that with bracket indexing. And there I've got the two strings in question, and if I stare very hard at them, I might be able to convince myself that yes, indeed, there's only one character different. I can't see which character it is at the moment, but I believe the computer. I think it's this P here is different from this X here. So then let's take my own advice, go and read the puzzle description very carefully. What we actually have to find is which letters are common between the two correct box IDs. So I don't just want to find the strings themselves. What I want to find is, in the example, the two strings were FGHIG and FGUIG. I want to find the strings with the differing character removed. So I've got the two strings. I could proceed from this point and then again take these two strings, work out where they're the same, and use that to mask one of those strings. But you know what? I'm getting that feeling again that this is all getting a bit messy, and maybe there's a better way. What I'd like to do is to go right back to the start where I was doing an outer product selfie on my list of strings and think, is there something better that I could have done in my outer product in the first place? Now that I know what kind of result I want for a given pair of strings, I want just the characters that are common. So what if I do that right up front? What if I take the characters that are common between two strings and use that to compress one of them, one or the other of them, it doesn't really matter, I'll get the same result. So now, instead of getting a big Boolean matrix telling me the coordinates of the result I'm interested in, now I'm going to get a vector of possible result strings, and I'm looking for the result string of length 25, because I know all the inputs had length 26. So the result for two strings that differ in exactly one place will just have 25 characters in it. So, for example, I could take this matrix, I could linearize it, and then perhaps say get the length of each of the strings in it, ask which of them have length 25, and use that to compress the list. And sure enough, here we've got our answer. Again, as before, it occurs twice because each of the pairs of strings is considered in either order. And as I said, there's nothing about the puzzle input, there's nothing about the data itself that says there would only be two matches. It's only because the description of the puzzle has told me that I know there's only going to be a unique solution. And indeed, if I ask for the unique solution, there we are, there is only one. And I can paste that. So this solution is making me feel reasonably good. The only thing I still don't like about it is it's got this number 25 in it. And if I present this solution to somebody else who's got some different input, maybe all their strings are of length 30. I don't know. So I don't feel too good about that. So if I was going to pursue this further, I'd start thinking, is there an even more elegant way that I could perhaps I like this list of all strings here. Maybe I shouldn't have tried to display that, but I want some more clever way of processing that result that doesn't involve me knowing that that the result is going to have length 25. Let me just interrupt this. And I'm not going to take this any further, but I would say, you know, if you are interested in monument quality code and publishing your solutions, that would be the next thing I would think about. And I'd be interested to see other people's solutions to that particular problem. The interesting thing about this, I think, is that seeing what the exact form of the solution that you have to submit is can make you go back and think again about exactly how you were tackling it in the first place. Sometimes you find yourself going down these rabbit holes and you just think, hang on, the whole thing's getting too complicated. Is there a simpler way I could have done this? A way that I understand better and would be happier presenting? Now, I'm going to leave that one there, as I say. I won't go any further with that particular puzzle. And I don't want to show you too many more puzzles. Day 3 happens to be a nice one. I know that works out well in APL, has some nice matrices. It would be a very good one to go off and have a look at next. I just want to show you one more thing, one more puzzle that is, which is to skip ahead a bit all the way to the first part of day 25. Now, day 25, again, you have to know how to read the input. You're going to get a list of fixed point in space-time. The list of fixed points in space-time, your puzzle input, is a set of 4-dimensional coordinates. And you need to find the number of constellations of points in that list of points. It's giving you the coordinates of some points in 4-dimensional space. And what is a constellation? 2 points are in the same constellation if their Manhattan distance apart is no more than 3. Or if they form a chain of points, each a distance no more than 3 from each other. Now the Manhattan distance between 2 points, if you imagine 2 points on a square grid, one down at the bottom left and one at the top right, if you imagine an overhead map of Manhattan with the grid of streets, the Manhattan distance is the distance you would need to travel on that grid to get from one point to another. So to get from the bottom left to the top right, you can't just go diagonally. You have to travel along streets, or as a rook would on a chessboard. So you have to travel along and then up separately. So mathematically, to find the Manhattan distance between 2 points, you need to know the absolute distance between them in each dimension, and then you need to sum those absolute differences. Yeah? You take the coordinates of 2 points and find the sums of the absolute differences between each item of those coordinates. So what I really want to show you is the input to this puzzle. I've already downloaded this one. Let's take a look at it. The first of the quad nget of day 25.text. Whoa, that didn't work. That's because I forgot the all-important 1 at the end. So here we are, character vector for each row of input. Let's put that in P. Let's look at the first line of input. It's the numbers -6 to -8 and 3. Can we just execute this string to get the numbers we want? Well, no, we can't, because these are normal minuses, because the way that APL uses a high minus as a unary thing, and the normal minus function applies to everything to its right. This is not giving us what we want. What we need to do is take this string here and somehow split it into its separate fields. So you could split it on the commas, maybe. You could probably work out some APL that would do that. But what I would like to recommend to you is that you learn how to use quad R and quad S. These are regular expression search and replace tools. And again, I'm going to show you a very, very simple case of this that I find invaluable for 95% of all of the kind of input processing of these simple text files that I have to do. So let me start with the unprocessed input here. What I want to do is apply quad s to each vector in that thing. Quad s is an operator, it's got two operands, which are on the left a regular expression that you're going to be searching for, and on the right, well, I'm just going to use a simple placeholder string. There are lots of things you can do with the right operand. For our purposes, I'm only interested in searching for regular expressions and returning the text that match that regular expression. That's what the ampersand means. So on the left is a regular expression. I don't really have time to explain what a regular expression is if you're not already familiar with them, but there are loads of resources for that on the web. I'm just going to write a simple regular expression that matches each of the individual numbers, that is the things in between the commas. And I reckon each of those starts with a minus sign, which is optional, the question mark here means optional, followed by a decimal digit, that's anything from 0 to 9, but let's say we want to match one or more decimal digits, so we can cope with 2 or 3 digit numbers. If I hit enter on that line, you'll see what it's done is I've now got an extra level of nesting in my data. Each line has now been split into a number of fields that match that regular expression. And now each of those, even though they use a normal minus instead of a high minus, each of those is something I can easily apply execute to. So I'm going to apply execute not just to each line, but to each field within each line. And now this is the kind of data I want. Now I've got for each line, a simple numeric vector of the numbers in that line. And this is what I'm going to work with. Now, the problem was to find which pairs of points are within a Manhattan distance of no more than 3 from each other. So this is yet another outer product kind of thing, or at least there are other ways of solving it, but to me it feels like an outer product kind of thing. I'll just name the processed input there. I want to do for all pairs of input, what do I want to do? Well, the first step in finding the Manhattan difference is just to find the absolute difference between two coordinate tuples. So I'm just going to do a plain old subtraction on every pair. Let's see what that looks like. Okay, so for every pair of points, I've got the difference in each coordinate value. You'll notice that along the diagonal of this matrix represents comparing a point with itself, and as you might expect, it is at a distance 0 from itself, but that's okay, that doesn't matter. Now I said I wanted the sum of the absolute differences. There are the absolute differences, and if we want sums of absolute differences, let's stick up plus reduce for each of those. So now we're getting somewhere. Now we've got a matrix telling us the Manhattan distance between each pair of points, which is a very good starting position. Incidentally, there's a message on the chat suggesting better ways of processing the input, which is great. I suggested doing this regular expression to match match every sequence which looks like a number to me. There was something going through my mind as I wrote this was, well, rather than trying to match the number, why don't I just match every sequence of characters which is not a comma, which I can write like that, which is slightly shorter. What I think Morten has just posted on the chat is something even better. Rather than searching for strings that match a regular expression, if I change this to a quad R, I can search for a very simple regular expression, the normal minus, and replace it with another very simple string, the high minus, and now I get strings that I can process very easily with APL. I can just do an execute each on those, and now I've got the data I wanted to work with again. So, great, that is much simpler. Back to our Manhattan distances. So here we have a matrix of the Manhattan distances between each pair of points. The question was asking where that is no greater than 3. So now we're down to a matrix where, well, okay, most of the points we could see here were at quite large distances from each other. As you might expect, the diagonal of this matrix represents points that are coincident, so they are definitely no further than 3 from each other. If we just look at a bit more of this matrix, okay, it's hard to see, your eyes are glazing over, but here are the ones on the diagonal, and you might just be able to spot, if you look carefully, there are some off-diagonal ones. This means points that are different, but are still within a distance of no more than 3 of each other. So, okay, we've got, that's interesting, that's the points that are close to each other, but the description of what forms a constellation is at pains to point out that to be in the same constellation, 2 points don't necessarily need to be that close to each other, as long as there is a chain of points from one to the other, where each one is within a distance 3 of the previous one. Now, at this point, what this says to me is it's a transitive closure problem. Now, if you're not already familiar with transitive closure, and in particular transitive closures of Boolean matrices in APL, that might not have occurred to you straight away, but let's think it through a bit. This matrix is showing me which points are within distance 3 of each other. The next step on from that is to say, well, okay, maybe I want to get from a point I. So in this matrix, if I have 2 points I and j, then the entry in the matrix at position ij tells me if they're close enough to each other. What if I want to get from a point I to a point k via some intermediate point j? How are we going to solve this? Well, the answer is you want to, points I and k are close enough to each other if there is any point j at all in the whole list of points which is both close enough to I and close enough to k. And if you think about what this means for the Boolean matrix, what we're looking for is, if you take row I of the matrix and column k, we're looking for any point in that row and that column where there is a 1 in the corresponding positions. And what that leads you to is, instead of just this matrix that I've produced, doing something like an or and reduction on it with itself. Order and reduce selfie. So perhaps we can see in the original matrix how many points were close enough to each other. Okay, so there are about 3,000 of them. That's including the 1,200 points we started with, which are all close enough to their self. If we do this order and selfie on it, okay, so we've got some more points that were close enough once you consider there might be one intermediate point to get there. What if we keep going though and try and get all points that are close enough if you consider 2 intermediates? Okay, there are more and more that are close enough when you take this into consideration. And what this leads you to is repeating the order and selfie until looking at more and more intermediate points doesn't help you bring any more of your original points into the same constellations. So if you know about transitive closures of Boolean matrices, you may have seen almost this exact same thing before. You get an order and selfie power match to keep running it until you reach a fixed point and you're not getting any further progress. Now, what is this matrix that we've got? It's got a load more ones in, as you might be able to see if we look at the top left corner, or perhaps more of the top left corner. Each row of this matrix, now you see some of these rows have got a lot of ones in them. Each row in this matrix is now a Boolean mask of which of your original points were in the same constellation as that particular point. And you'll see that for any two stars, 2 points that are in the same constellation, obviously those rows will be identical because they're talking about the same constellation, which will be the same list of points which is in that constellation. So, how do we work out how many different constellations there are? Well, this is now simple. It's the number of different rows in that matrix. Since we're using version 17, I can apply unique to a matrix and it will give me just the unique rows. I can then count how many there are. 386 unique rows in this matrix. And that is the answer that we're looking for. How many constellations were there in this list of points? The reason I show you this is that this one line of code, it's not that I'm desperate to get it in a one-liner, but this one-liner firstly contains an awful lot of cool things that you can do in APL. Secondly, every part of this I think you can explain with reference to the original problem. I can chop this up into small chunks and explain clearly what each one of these is doing. And thirdly, you might think about how close do you think this is to monument quality code? Are there things you would do to improve this? One thing you might think about is the fact that this P is a nested vector of vectors. From an efficiency point of view, you might be tempted to mix it and get a flat numeric matrix and then try and do all your operations on that if you're concerned about the efficiency of your solution. That, I would suggest, is a very good exercise to go away and try, and you may find that it's very good practice for using the rank operator. Now, I'm conscious that I'm overrunning. There were a couple more things that I wanted to show you. I think we've seen enough APL code and I've solved enough problems on your behalf. One thing I wanted to show you before we part is, as well as the website itself, there is a very active discussion of Advent of Code on Reddit. So if you look on the subreddit called Advent of Code, all one word, this is a discussion board. There is a lot of general chat about problems and how to solve them. But in particular, for every day's problem, there's what they call a solution megathread. It may not be obvious, but this little calendar here for December 2018 is a set of links to the solution megathreads. So, for example, if I click on day 2 here and wait for the internet, what I see is a lot of people posting their solutions for day 2's problem. Now, you might remember we did that in 1 or 2 lines of APL. Here's somebody who's done it with regular expressions in Perl. Here's someone who's done it in what they describe as horrendous Python. It's fairly short, but it's still fairly horrendous. Here's someone who didn't want to use a programming language, so they did it all in their text editor, again, using regular expressions. And here's somebody, this is interesting, this is apparently very clean, nice Python code. All I can say about this is this guy must be very fast at typing, because despite typing in over a page of code, he was fast enough to be the 20th person to solve the problem in the world. And I can tell you, I got nowhere near that fast, even though I only had to write 1 line of code. So, Reddit is a great resource. Obviously, it contains lots of spoilers, but you're free to look at those or not as you choose. The other site I wanted to show you was, I said a lot of people publish their solutions. I've published my solutions to nearly all of the 2018 puzzles and some of the puzzles from 2017. So what you'll typically find is people push a GitHub repository. Here's mine. If you go to GitHub and search, you'll find hundreds of others in all kinds of languages. In my one, I've got for every day's problem, I've got a text file with my personalized input, and I've got a .dialog file with the APL solution. In some cases, these are cleaned up solutions, obviously. In some cases, I spent a bit of time cleaning them up and came up with more than one way of solving the problem. So, for example, day 14, I've got a p14.dialog. There's also a p14 fast, which is based on some ideas I had later where I came up with a faster solution for the same problem. So by all means look at those if you want to, but obviously they contain spoilers, so I'd suggest you might want to try and solve the problems first yourself before going and looking at other people's solutions. And that is really all I have time for and all I wanted to say to you. I hope I've inspired some of you to look at the puzzles and try solving them for your own education. Perhaps I've inspired some people to play along. Hopefully this December 2019, the competition will be on again and we might see a few more APL entries. And if you have no interest in solving puzzles, then maybe I've inspired you to try and think about, as clearly as possible about the problem you're trying to solve and whether you truly understand the code that you're writing to solve that problem. That's all from me. Thank you for watching. The next webinar will be on 4 weeks from today, on the 21st of March 2019. The topic is as yet undecided, so if you have suggestions or any other general comments about the webinar, please do get in touch. You can email webinar@dialog.com. I'll leave you with some useful links. That's all. The useful links will be in the description down there. And that's all from me. Thank you for watching.